Hello. So today I wanted to talk to you all about what a photon is and also what are its unique properties. When you think about it, we start in basic chemistry and physics classes and we talk about light in a very defined and set way. We generally talk about it as a wave. What I mean by wave is just your classical wave. You start and you've got an amplitude and you've got, it's following this wave-like property, It's got a certain amount of energy normally, dependent on this amplitude. And this is kind of how we characterize light for much of the time that we go through grade school and then into universities and here at BYU. And so today I want to talk about how a photon is actually more like it actually has two properties that can be stated as wave properties, but also particle properties. And so today we want to talk about how this can happen, how we can have both of these in one discrete packet called a photon. So first I wanted to start off with a little bit of history about how we know that this is occurring. So we'll call it the history of wave/particle duality of photons. First, to define what a photon is going to be a discrete packet of light. And this idea of a photon was first theorized long ago, but was really solidified by a famous scientist that we all know, and that would be Albert Einstein. And he came up with the idea that photons were the discrete packets of energy that all light was composed of. And the reason why that they figured this out was that you had certain experiments being done by people like Planck and other scientists that were trying to discover why there were certain effects that were occurring in this world. One of them was called the photoelectric effect. Now, we probably heard about this in Chem 105, maybe in other chemistry classes or other physics classes, or you just heard about it. But the photoelectric effect is really, really unique. What they tried to explain the photoelectric effect was, or I guess we'll just start with what is the photoelectric effect. So the idea is they have a piece of metal, and then you have different colored waves of light that will come in. So in this case, we have red light, okay? And on the surface of this metal, you're going to find electrons that are on the surface, okay? So we'll signify them by these circles, okay? Calling these an electron, okay? And these packets of, or these waves, as they used to think back before they understood this particle-wave duality, is these waves would come in, and their initial theory is that if you had a high enough energy, if you had enough of like a red type of light, or the red frequency of light, that you would be able to excite these electrons and you would be able to get them to eject off. Now, what they observed was that red light, no matter how bright, how intense, how many rays were going in, it could not cause these electrons to shoot off or fall off of this piece of metal. They just couldn't do it. And so this to them was crazy. They were like, why? And so that is when they started thinking about, well, what would cause this? And so what Albert Einstein talked about, we got Einstein here, he says that what is happening is that photons of light or discrete packets of light are what's happening here. And so in red light, the amount of energy that you have in this packet of light here is not high enough for the electron to be ejected. But let's say that we had some blue light, which is a higher frequency and thus has more energy. And if you were to shoot it at the same electron, it would be able to excite that electron. And it would fly up like that. So, with that information, he went on to say that a photon is quantized. And for something to be quantized, it means that it's almost like an example they always use is it's like a staircase, okay? And so each packet or each photon of light has a certain amount of energy, okay? And so it can be at one staircase or two staircases or three cases. It's three staircases, it's 3 steps up, but it can't be in between. It can't be right there, okay? It's impossible. You just can't be right there. And so a photon here is having that discrete packet of light with a certain amount of energy. And so the way that they eventually expressed this was working off of Planck's work, but they said that the energy of a photon is equals to Planck's constant, h, times the frequency. And so it was very hard how they found Planck's constant, but they found it. And at times the frequency or the wavelength. And so this was, or the frequency of the electromagnetic radiation or light that they're shining. And so this is how you would find the energy of a photon. And the energy of that photon is in discrete quantities. There's a certain amount of energy. If you were to have a detector that could detect very, very small amounts of energy, you would be able to get that detector to detect a certain amount of energy for one photon, but it would have to go up to this amount of energy here, and you would not be able to get an energy amount in between nothing and that. It would just be impossible, given a frequency of light. And so all of this comes together to say that it's really hard to understand what a photon is and how it works. But we do understand that it acts as a wave, like we've discussed in this video, like this, but it also acts as a quantized piece of or a particle that has particle properties with also these wave properties, which makes it really hard to try to talk about. And so a good analogy that I've thought up is how sometimes if you think about it, it's almost like a non-Newtonian solid. I mean, this is a very kind of convoluted way of thinking about it, but non-Newtonian solids, it'll be like this weird, glue type thing. And if you hit it really hard, if you punch it, right, it will be really, really hard. And it'll be like a rock, that you're trying to punch. But if you were to sink your fist in slowly, what would happen? And if you think, instead what would happen is you would have it sink in slowly, and it would almost be like a putty, or I don't know, it would feel very soft and be easy. And so that difference is it's the same property, it's called a non-Newtonian solid, to where it can have two distinct properties, in different circumstances. And the only thing that is different about a photon is that the photon is going to have both wave properties and particle properties at the same time. This is something that we really can't understand or conceptualize that well, but it is what is occurring and is what explains things like the photoelectric effect and other things. So, thank you for listening to this video, and I hope that this might help you understand photons and their wave and particle duality a little better. Thank you.